Hello students, I'm Dr. Ashma Srivastav from Department of Chemistry, JSS Academy of Technical Education. The topic of my today's lecture is Introduction to Spectroscopy. Spectroscopy is Unit 2 of Chemistry AKTU syllabus, and in this unit you have to study the basics of spectroscopy along with 4 absorption spectroscopies, which are UV visible spectroscopy, IR spectroscopy, microwave spectroscopy, and Raman spectroscopy. Today's class is devoted to understand the basics of spectroscopy. The learning objectives of today's class can be broadly divided into 4 heads. Number 1, to define spectroscopy and to study the characteristic features of electromagnetic radiation. Number 2, to understand the relationship between frequency, wavelength and wave number of electromagnetic radiation. Number 3, to interpret the characteristics of two spectroscopies, that are absorption spectroscopy and emission spectroscopy. And finally, to state and derive the Lambert-Spear law. Now to begin with, we'll take up the definition of spectroscopy. Spectroscopy deals with the study of quantized interaction of electromagnetic radiation with matter. Or simply I can say, it is the study of interaction of light with matter. Now what is matter? Matter is that organic compound whose structure we want to determine. So with the help of spectroscopy, which is considered as a very powerful tool, the structural determination of the compounds is done. Now, as we are dealing with electromagnetic radiations while doing the spectroscopic studies, we need to understand what is electromagnetic radiation. In simple words, electromagnetic radiation is a simple harmonic wave of electric and magnetic fields fluctuating perpendicular to each other. There are various forms of electromagnetic radiations. For example, visible light, ultraviolet radiation, infrared, X-rays, microwaves, radio waves, gamma waves, etc. Now to characterize the electromagnetic radiation, we need either of these 3 parameters, which are frequencies, wavelength or wave number. With the help of either one of them, we can characterize the electromagnetic radiation and we can talk about its energy. Now we'll take them one by one and then we will see the interrelationship between them and their interrelationship with the energy of the electromagnetic radiation. The first parameter is frequency. It is denoted by the symbol nu and it is defined as the number of waves which can pass through a point in 1 second. It is measured in cycles per second or hertz. The second parameter is wavelength. Wavelength is denoted by the symbol lambda and it is defined as the distance between two consecutive crests or troughs of a wave as shown in the figure. It is measured in various units which are micron, nanometer, angstrom, etc. The third characteristic is wave number. Wave number is denoted by the symbol nu bar and it is defined as the number of waves which can pass through a distance which is per unit length and it is usually 1 centimeter. It is the reciprocal of wavelength and is expressed in centimeter inverse. Now let us see the relationship between the 3 characteristics, that is frequency, wavelength and wave number. Energy of electromagnetic radiation is given by the equation E is equal to h nu, where h is the Planck's constant and nu is the frequency. There is another equation where nu is replaced by c by lambda. So we see that energy of the electromagnetic radiation is directly proportional to the frequency of the radiation and inversely to the wavelength of the radiation. So it means that if the energy of electromagnetic radiation is high, its frequency will be high, but its wavelength value will be low. The another expression is there which is between wave number and wavelength, we just see that it is the reciprocal of wave number, is just the reciprocal of wavelength. So wave number is inversely related with wavelength, or we can say that wave number is directly proportional to frequency and to the energy of the radiation, whereas it is inversely, wavelength is inversely proportional to wave number as well as frequency. Now let us see the electromagnetic spectrum. Based on the energy of the electromagnetic radiation, the entire electromagnetic radiations have been divided into several regions, and the arrangement of all types of electromagnetic radiations in order of their increasing wavelength or decreasing frequencies is known as the electromagnetic spectrum. Electromagnetic spectrum ranges from very short waves to very long waves. It starts from cosmic rays or gamma rays and extends up to radio waves. In this figure, we can see that it is starting from gamma rays and ending to radio waves. So as we are moving from left to right, the energy of these radiations is decreasing, the frequency is decreasing, but the wavelength is increasing. So as we move from left to right, the wavelength is increasing, frequency is decreasing, wave number is decreasing, and energy is decreasing. In this next picture, which is again of electromagnetic spectrum, I have tried to show you the visible part of the electromagnetic radiation. As you can see, that visible region is a very small portion of electromagnetic spectrum, and here it has been magnified to show that it extends from violet band to red band, and the wavelength of visible region is between 400 to 780 nanometer. Now let us come to one of the spectroscopy, which is called absorption spectroscopy. Now what is absorption spectroscopy? Absorption spectroscopy means that in this spectroscopy we study the absorption of light by the molecule under study, and this absorption of light is used to induce certain transitions in that molecule. What sort of transitions? The transitions can be either electronic or vibrational or rotational. So with the absorption of electromagnetic radiation, the electronic, vibrational or rotational transitions takes place in the molecule. Now the energy which is required for these transitions is quantized. What does it mean? It means that only the radiation which is supplying the required quantum or photon of energy is absorbed, and the remaining portion is transmitted. The wavelengths or frequencies of the absorbed radiations are measured with the help of an instrument which is called spectrophotometer. Now this figure shows the instrumentation of spectrophotometer. What is spectrophotometer? It is recording that what part of a light is absorbed by the sample when it is passed through it. Now we can see that it begins with the light source. Light source means what is the region of electromagnetic radiation which we have chosen. Let us say we have chosen the visible portion or visible light of the spectrum. Then it means that the wavelength of the light which is coming out from this light source is from 400 to 780 nanometer. And this light is allowed to pass through the collimator, which is lens, which concentrates the light and allows it to travel in parallel direction. When this parallel rays are passing through the prism, which could also be a grating, then the splitting of that incident beam of light takes place, and this splitting of light takes place into different wavelengths. So when the grating is used, it splits the incident beam of light into different wavelengths. Then with the help of a device which is called filter or wavelength selector, suitable wavelength is chosen and it is allowed to pass through the sample which is taken in a cell which is called cuvette. The intensity of the light before passing through the sample is termed as I naught, that is intensity of the incident light. No absorption of the light has taken place when I naught is I naught has reached the sample. Then after passing through the sample, there is absorption of that particular wavelength of light, and the intensity of the transmitted light will definitely be lesser than the I naught value, which means absorption would have taken place while the light was traveling from the sample, from one end of the sample to the another end. The point to be remembered is that we have fixed the wavelength of the light, energy is fixed, only the change in intensity is observed when the light is passing through the sample. Then when the light comes out of the sample, the intensity is decreased, and that intensity is measured, that what is the reduction in the intensity of the light, with the help of a device called detector. Then the detector digitally records the absorption of the light, and on the display we can see the absorbance value. What is absorbance? Absorbance is the ratio of the incident light to the transmitted light. Now next we'll take absorption spectrum. Absorption spectrum is the plot of intensity of absorbed or transmitted radiation versus their wavelength or frequencies. Such spectra which are obtained by the absorption of electromagnetic radiations are called absorption spectra. The light is passed through the sample, one particular wavelength is selected, and then there is reduction in its intensity, which tells us that that particular wavelength has been absorbed. Then there is a series of another wavelengths which are also passed through the sample, and the data is recorded. So in the absorption spectrum, we are plotting those wavelengths on which the absorption of light has been taken place. There may be some parts of the light or that spectrum which may not be absorbed by the sample, so that is a flat region of the absorption spectrum. The absorption spectrum which we are going to get in UV visible, IR, Raman and microwave spectroscopy, they all are absorption spectrum, because all these spectroscopy are absorption spectroscopy. Absorption spectroscopy, why? Because in all these spectroscopies, what we are studying? We are studying that what part of the spectrum or light, electromagnetic radiation, has been absorbed by the sample, and from that absorption we are plotting a graph which is called the absorption spectrum. The plot is between the intensity of absorbed light to the wavelength of the light which has been absorbed in a simpler sense. Now this figure shows the absorption spectrum of some compound, and here on the y-axis there is absorbance and x-axis is wavelength. Absorbance means that what is the intensity of the light that has been absorbed by the sample. Now in this figure we can see 4-5 bands or 4-5 peaks. These peaks are telling us that at these wavelengths the light has been absorbed by the sample. Now why the light has been absorbed by the sample? Because the wavelength or energy of this light was corresponding to the same energy gap between the various levels of the molecule. They can be electronic energy levels, they can be vibrational energy levels, rotational energy levels, and this light, the energy of this light or this wavelength is matching with that energy gap between the levels of the molecule, and hence it is absorbed. And this spectrum is telling us that at wavelength ranging from 300 to 400, the four wavelengths have been absorbed by the compound, and these four or five bands are signifying that this much number of transitions have taken place in this molecule upon the absorption of light between 300 to 400 nanometer. Now let us see the energy level diagram for the absorption spectrum, and it will explain the entire thing which I have discussed till now in absorption spectroscopy very clearly. Now let us consider two energy levels of a atom or molecule. The one with lower energy is called the ground state energy level, that is denoted by the symbol E1, and the one with the higher energy is called the excited state energy level, denoted by the symbol E2. So there are two energy levels, E1 and E2. E1 is the ground state, E2 is the excited state. Now when an atom or molecule undergoes the transition from the lower energy level to the higher energy level by the absorption of the photon of energy h nu, provided that h nu is exactly equal to the energy difference between the two levels, then absorption of light takes place. See this figure. E1 and E2 are two energy levels present in the molecule. E1 denotes the ground state, E2 denotes the excited state. The energy difference between the two levels is delta E. Now when we are passing the light through this compound, if the energy of the light is matching with this h nu, then it will be absorbed and it will excite the molecule from its ground state to the excited state. By the absorption of that light which was supplying that photon h nu, only the excitation is going to take place, and that leads to the absorption band. Now after understanding the absorption spectroscopy, we can very easily understand the emission spectroscopy, which is having the opposite story. Now in emission spectroscopy, what we are recording? We are recording that when the molecule jumps from the excited state to the ground state, what part of the light it is emitting. So the spectra which are obtained by the emission of electromagnetic radiation from the excited state of the compound to the ground state are called emission spectra. And example is given, atomic emission spectra. The excitation, the molecule is generally present at the ground state, so we have to excite it first by some process, and that process can be a thermal process or electrical process. We have excited the molecule to the higher energy state, we have sent it to the excited state. Till now we have not done any study. Now when the molecule is going to jump from the excited state to the ground state, or when it will come back from the excited state to the ground state, we are going to record the intensity of the light that is emitted by the molecule, that what energy or what wavelength of the light has been emitted by the molecule is recorded, and then it gives us the emission spectra. So excited substance when comes down to the ground state emits certain radiation having the wavelength of fixed wavelength of frequency, and then it is recorded with the help of spectrophotometer, and it leads to the emission spectrum. See this figure. This is the energy level diagram for emission spectrum. E1 and E2 are the ground state and excited state of the molecule. The molecule is sent to the excited state by any thermal or electrical process, and now when it is coming back from the excited state to the ground state, we are recording that what part of the light it is emitting, and this gives rise to emission spectroscopy and emission spectrum. Now the summarization of absorption and emission process we can see through this figure. A molecule can jump from one energy level to the another energy level by either absorbing or emitting a photon of energy that separates the two energy levels. So absorption of photon, if we are doing this study, what part of the electromagnetic radiation has been absorbed by the molecule to induce the excitation from the ground state to the excited state, then it leads to absorption process or absorption spectroscopy. And when we are studying that when the molecule comes down from the excited state to the ground state, what energy of photon it is emitting, if we are studying that, then it is termed as emission spectroscopy. So this figure clearly shows the basic difference between absorption and emission spectroscopy, and as I said earlier, they work in opposite manner. Now in this slide, or through 1-2 more slides, we will study that what happens when the part of the electromagnetic radiation interacts with the molecule. The molecules undergo the various processes like rotation, vibration, electronic transitions or nuclear transition upon coming in contact with the light, or I should say when the molecule is irradiated with the electromagnetic spectrum or region, one part of the electromagnetic spectrum, then these processes take place. Now these energies, the energies which are required for these processes are different, and hence the molecule interact with different regions in different ways. If we are using one particular region of the spectrum and we are interacting it with our sample, then one type of transition will take place. It is not possible that we are using infrared radiation and it can cause nuclear transition, electronic transition, rotational, vibrational, every transition, every process will not take place. Certainly, what will happen, that one part of the spectrum is having certain energy and that will be responsible for one or two processes. Let us see how. The radio frequency region have the very low energies, and this much energy can only cause the transitions between the nuclear magnetic energy levels, which are very closely spaced. And the example for this interaction is NMR and EPR spectroscopy. Then second comes the microwave. The energy of the microwave is between radio waves and infrared radiation. So it corresponds to the energy gap between the rotational energy levels of a molecule. So upon the absorption of microwave radiation, the rotational transitions takes place. And thus this region of the electromagnetic spectrum finds application in rotational spectroscopy. Third one is infrared radiation. Now this energy is equivalent to the energy gap between the vibrational levels of the molecule. So when we are irradiating the molecule with infrared radiation, vibrations takes place, or I should say vibrational transitions takes place in a molecule, and thus this region finds the application in IR spectroscopy, which is also called vibrational spectroscopy because it is leading to vibrational transitions. UV visible light. UV visible light or UV visible region has the energy which can cause the electronic transitions of the in the molecules, and this finds the application in UV visible spectroscopy. So when we will be studying the UV visible spectroscopy, what we will be studying? We will be studying the electronic transitions which will take place when the UV or visible light is absorbed. The final example is given for X-ray radiation. As all of us know that X-ray radiations have very high energy. So they have the capability to cause the transitions in the internal electrons of the molecule. Where in case of UV visible, the valence electrons were excited. Here, with the help of X-ray, the internal electrons can also make the transitions, and hence with the help of this interaction we can get the information related to the electrons present in the inner shells of the molecule. So all these spectroscopies are, or all these interactions are giving us some or the other information regarding the structure of the molecule, and hence we can use them to completely know the complete structure of the molecule. Now next we will take up the Beer-Lambert's law or Lambert-Beer's law. This law governs the absorption spectroscopy. Now what is the statement of this law? It states that when the monochromatic light is passed through the homogeneous absorbing medium, this homogeneous absorbing medium is a solution containing the solute which is going to absorb the light. So when the monochromatic light is passed through a homogeneous absorbing medium, the rate of decrease in the intensity of light with the thickness of the medium is directly proportional to the concentration and intensity of the incident light. Now what we see here, we see a cell containing the solution, and that is termed as the absorbing sample of certain concentration. And from this solution, the incident light or light having the intensity I naught is passed. The path length of this sample is, let us say, x centimeter, and through this x centimeter the I naught is passing. Now when the light is coming out of this sample, there will be reduction in the intensity of the light. You can see that the arrow, blue arrow, has narrowed down, and I naught is the arrow which is shown by for I naught, it is broader. So as the light passes through the sample, there is reduction in the intensity of this light. And what the Lambert-Beer's law is telling, that rate of decrease in the intensity of the light with respect to the thickness of the medium, that is x centimeter, let us say, is directly proportional to the intensity of the light, that is I naught, and directly proportional to the concentration of the sample which we have taken. Now we will derive the relationship for the Lambert-Beer's law by using this statement. So rate of decrease of the intensity with the thickness of the medium, we can write it as minus di by dx. Dx is a very small distance which will be travelled by the light, and x centimeter is having several dx in it. Okay, so minus di by dx means rate of decrease in the intensity of light with the thickness of medium. Now it is proportional to the intensity of the light I and concentration of the medium C. So when we remove this proportionality sign, then we are going to place a constant, that is k. So minus di by dx is equal to k I C. Okay? K is the constant, I is the intensity of the light, and C is the concentration. Now upon rearranging this equation, we can write minus di by I is equal to kc dx. Now we will integrate the both sides of this equation. The intensity component will be integrated between I naught to I, that is intensity of the incident light and intensity of the transmitted light, and the right hand side expression dx will be integrated between the limits 0 to x. 0 when the light has not travelled any distance, and x centimeter is the distance which it has to travel. Now upon integrating and upon solving this entire expression, the final expression that we are going to get is log I naught by I is equal to k 2.303 into c into x. Now what is this I naught? I naught is the intensity of the incident light. I is the intensity of the transmitted light. K by 2.303 can be replaced by another symbol, that is epsilon, and this symbol is termed as molar absorption coefficient, or simply the absorptivity coefficient. C is the concentration of the medium and X is the path length. Now if we keep the path length constant, then we can see that A, that is absorbance of the sample. What is A? A is that log I naught by I. So it can be substituted by a simple alphabet, that is A, and A stands for absorbance. Absorbance is directly proportional to the concentration of the medium and the path length. And if we keep the path length constant during our study, then what we will find, that absorbance is directly proportional to the concentration. Higher the concentration, higher will be the absorption of light, or higher will be the absorbance of the solution. So now we can see this graph. This graph is called the calibration graph, and a simple Lambert-Beer's law graph. Here the absorbance is plotted against concentration. So we get a linear graph, and this linear graph is telling us that as the concentration increases, the absorbance value increases. Okay? So you can see in the figure, it has been shown that incident light has passed through the sample. It has covered the distance. L is shown here. We have taken X as the distance, and the intensity of the transmitted light is reduced, and absorbance value is given for one particular point, 0.4. Now we can also derive some other relationships between transmittance, absorbance. Through this slide we can see that. Now on the top of the slide it has been written that transmittance is the ratio of the intensity of the sample. Transmittance is the ratio of the intensity of the light transmitted by the sample to the intensity of the light incident on the sample. That is, T is equal to I by I naught. I is the intensity of the transmitted light, I naught is the intensity of the incident light. Now just to get more relationships between absorbance and transmittance, let us take the log on the both sides and log to the power base 10. So what we will get, log T is equal to log I by I naught. Now if we put a minus sign before log I naught by I, then it means the same, that is log I by I naught, and we will get a relationship that log T is equal to minus A. Further we can write it as log T is equal to 10 to the power minus A, and A is nothing but absorbance, so we can substitute it with epsilon Cx. So 10 to the power minus epsilon Cx. So this is another relationship which we get between absorbance, transmittance, concentration, path length, etc. So absorbance is equal to minus log T. Now to derive one more expression of percentage transmittance, let us look at the expression given below it. To write percentage transmittance, what we have to do? We have to multiply the transmittance with 100. And then we have to substitute this expression in A is equal to minus log T. And upon substituting these values of percentage transmittance here, later on solving it, we will get that A is equal to 2 minus log percentage transmittance. So this is the another relationship which we get. So many relationships we are having, and we will be using them to solve the numericals based on Lambert-Beer's law. The one expression is that A is equal to epsilon Cx. The another expression is A is equal to minus log T. Then A is equal to 2 minus log percentage transmittance. So these are the three main expressions that we get by solving the Lambert-Beer's law in several ways. Now some interesting points to note. An absorbance of 0 at some wavelength means that no light of that particular wavelength has been absorbed. The intensities of the sample and the reference beam both are same. It means that I naught, there is no change in the intensity of the light when it is passed through the sample. So I naught by I will be equal to 1 and log to the power 10 of 1 is 0. So absorbance 0 when there is no absorbance, or sorry, when there is no absorption of light of one particular wavelength that is passed through the sample. An absorbance of 1, it means that when 90% of the light at that wavelength has been absorbed, which means that the intensity of 10% of what it would otherwise be. So when we are getting the absorbance 1, it means that 90% of the light has been absorbed and 10% is transmitted. So if in the expression I naught by I, intensity of the incident light is 100% and intensity of the transmitted light is 10%. That gives us 10 and log 10 is nothing but 1. So the value of absorbance ranges between 0 to 1. Now there are several drawbacks, limitations of Lambert-Beer's law. And Lambert-Beer's law, that is the linearity of that relationship, absorbance is equal to epsilon Cx, doesn't fit well under certain situations. The linearity is not obeyed in certain situations. And what are those situations? Number 1, the deviations in absorptivity coefficients of high concentration. If the concentration is higher than 0.01, then 0.01 m, then the linearity of this Lambert-Beer graph is not obtained, and it is due to the electrostatic interactions between the molecules which are in close proximity. The another reason for the deviation is the scattering of light due to the particulates present in the sample. Third reason is fluorescence or phosphorescence of the sample. Next, changes in the refractive index at the high concentration of the sample. Next is if we are using a non-monochromatic radiation. If we have not fixed the wavelength of the light while before passing it through the sample, then also there will not be any linearity for that Lambert-Beer's law relationship. And this brings us to the end of our lecture on the introduction to spectroscopy. We'll see you in the next lecture, where we will discuss the basics of UV visible spectroscopy. Thank you.